If determining the end behavior of power functions is making sense, then to move on to determining the end behavior of polynomial functions, in order to make that step, we really just need to add one relatively small piece, one relatively small concept to our process. So every polynomial function has a degree and a leading coefficient. The degree of a polynomial is determined by the term with the largest exponent. So wherever we see the highest power, that is our leading term, and it gives us our degree. And the leading coefficient is the coefficient of that same term. If we consider the functions f of x equals 4x to the sixth and g of x equals 4x to the sixth minus 4x to the fifth plus 2x, we can see that they both have the same leading term, they both have the same degree, and same leading coefficient. They're both sixth degree functions with a leading coefficient of 4. But if we first look at the graph of these two functions, we can see that they have very, very different behavior attributable to those additional terms that g of x has. But then what we have pictured in the graph on the right are those same two functions, only we've zoomed out. So now, instead of this largest function value being approximately 1, now our largest function value, is a little hard to read there, is 1600. So we've zoomed out a lot to see what's happening to these functions as our x value is getting larger. And what we can see is that the behavior of the graph that was very different in this region here, that's what we have on the left if we zoomed back in, kind of fades away. And as we're considering x headed to positive infinity and negative infinity, we're just considering very large x values. What we can see is that the behavior of this function is very similar in both cases. Headed to the same direction on both ends, and as we continue to zoom out those curves, we continue to get closer and closer together. What all of that means is that to understand the end behavior of a polynomial function, as x approaches positive infinity or x approaches negative infinity, those two functions behave very similarly for those extreme values of x as x gets larger. So to determine the end behavior, all we need to do is investigate the leading term. And we can see that here. 4x to the sixth, we have an even power, we have an even degree, and our value for a is positive. That means our function is heading to positive infinity in both directions. But once we look on a large enough scale, again, we see that the same thing is happening for both curves despite those additional terms. On the whole, or kind of over time, as those x values get larger and smaller, we start to see that behavior being very similar. So to identify the to identify the end behavior, we'll identify the degree, which in this case is 6, and the leading coefficient, which in this case is 5, and that's positive. All we need to do is look at this leading term and basically consider this to be like a power function. Whatever the behavior of 5x to the sixth is the behavior of this polynomial. So we'll consider as x approaches infinity and as x approaches negative infinity. The degree is even, so our function n of x should be headed to the same value in both directions. Our value for a is positive, so our curve is opening up. So our function is headed to positive infinity at both ends. In example 9, we need to start being careful here because we can get tricky with these problems. The term with the highest power is actually the second term, plus x to the fifth. That means this is a fifth degree polynomial with a leading coefficient of 1, which is greater than 0. Since we have an odd degree and a positive value for a, we're going to have a curve that looks like this, headed in opposite directions. That tells us that as x is approaching positive infinity, r of x will be approaching positive infinity. And as x approaches negative infinity, r of x will be approaching negative infinity. In example 10, we have a polynomial of degree 6 with a leading coefficient of -5. That means our curve is opening down. So as x approaches positive infinity, f of x will be approaching negative infinity. And as x approaches positive infinity, f of x will be approaching negative infinity. Again, we know those two directions are the same because we have an even degree. Then for example 11, our leading term is back in the first position, but we always want to make sure we're looking through all the terms for that highest power. Negative x to the seventh, meaning we have a seventh degree polynomial with a leading coefficient of -1, which is less than 0. So instead of the behavior that we saw in example 9, that behavior will be flipped to look something like this, which tells us that as x is approaching positive infinity, k of x is headed down to negative infinity, and as x approaches negative infinity, k of x is headed up to positive infinity.